Hey everyone, let's go over section 3.2, polynomial functions and their graphs. We want to start by defining what a polynomial is. So a polynomial is a function that has the basic form f of x is equal to some number times x to some power, and then we have an additional coefficient times x to a reduced power, and then another additional coefficient times x to yet another reduced power, and it keeps on decreasing in this fashion until we reach like our last coefficient here times x to the first power, and then plus a constant on the end. And then each of these a sub n sub i's, we could call them, or a sub i's. Each of these a's is a real number, and n is a natural number, like 7, 3, 400, something like that. Not -10, square root of 2, 1/3. That's not allowed for a polynomial. Now the coefficients could be, so that means that something like f of x equal to the square root of 2 x to the 10th minus pi x plus 37, that's just fine, and that's a polynomial. But something like g of x equal to 3 x to the 1/2, that's not a polynomial because of that to the 1/2. Same thing with h of x is equal to x to the square root of 2. Once again, that can't be possible. We have to have these natural number 1, 2, 3 powers of x. But the coefficients, any real number. Positive or negative is just fine for those coefficients. Okay, now if we're looking at functions with these properties, they all have a certain type of graph. This graph, let's just draw some axes here so we can kind of get a feel for it. This graph is smooth. What does it mean to be smooth? Well, that means they do things like this. There's no sharp corners. And funnily enough, smooth is a technical term in math. So that means something that does this is not a polynomial. And they're continuous, which we could think of as another way of saying that they're connected. So something like this, that's smooth up to a point, and then it comes to another point, and it's still smooth. Again, nope. That's not allowed. But something like this, that wiggles about a whole bunch, that's just fine. So no sharp corners, no gaps, or no holes. No corners, no gaps, no jumps, no holes. Nice, smooth, rounded corners and turns. The end behavior of a polynomial is really important. It's based on the degree of the polynomial, and that determines the overall shape. When x gets really, really big, x to the 4th is more important than x squared. So the leading order coefficient, the leading order term, that really determines the overall behavior of a polynomial. I had a professor who used to say that if you zoom out enough, every parabola looks something like that. And every cubic is going to look something like that if you zoom out enough. if n, our degree, is even, and our leading order coefficient is greater than 0, that's functions that look like this one right here. So the two n's are going to go up. And it's going to do all sorts of weird stuff in between. Or maybe it's just smooth. I don't know. But the two n's are going to certainly be pointing up like this in the same direction. Whereas if n is odd, and a sub n is greater than 0, they'll point opposite directions. So a sub n is greater than 0, so that means as x goes up, a sub n, x to the n, is going to increase too. So this end is going to go way, way up. And then the opposite end is going to go way, way down. And in the middle, it's going to do all sorts of weirdness, like it might loop around a couple times. But the ends are going to be pointed oppositely like that. What if we have n even and a sub n less than 0? That's something like negative 3 x to the 10th. Well, because it's even, the two ends are going to point in the same direction, but because we've got this negative sign, they're both going to be pointing down. And this is kind of that upside down parabola shape. So it might do something like that. That would be this case. And I guess the fourth thing we have to consider is that n is odd and a sub n is less than 0. That's something like negative 2x cubed. And that's the reverse of this. We recall how graph transformations work. It's really high on the negative side of things. It flips around, does some stuff, and it comes down and goes really, really low on the negative side of things. Think about negative 2 times 1,000 or 100,000 even cubed. That's going to be way negative. And the graph will overall look something like this. Let's just draw them a couple of times here. So this is something like this. This is something like this. This is something like this. And this could be something like this. All right. How do we find the zeros of these polynomials? In short, we have to factor. That's the only tool we have at our disposal. There are other techniques, but right now it's all we've got. And to be honest, it's just about all we ever have. So I'm going to find the zeros of this right here. We could call this f of x equal to negative x to the 4th plus 4x cubed minus 4x squared is equal to 0. Well, each one of these has x to at least the second power, so that's what I'm going to pull out. So we'll have x squared times the quantity x squared plus 4x minus 4 is equal to 0. So now it's this right in here in the parentheses, x squared minus 4x minus 4, that we're going to have to factor. I think that this right here is x, well, it can't be x minus 2 quantity squared now, can it? Because this is negative. And we've got, let's see here, negative 1 and 4 is 3. Negative 2 and positive 2 is 0. And my goodness, I think that just doesn't factor. What could we do with this? Let's try. So, whoops, no factoring. But it is squared, so I think quadratic formula. x is equal to minus 4 plus or minus square root of the quantity 4 squared minus 4 times negative 4 square root of that all over 2. So this is negative 4 plus or minus the square root of the quantity 16 plus 16 over 2. So that's negative 4 plus or minus the square root of 32 over 2. 32 is 16 times 2. So the square root of 16 times 2 is 4 square roots of 2. So this becomes negative 4 over 2 plus or minus 4 over 2 square roots of 2. This is negative 2 plus or minus 2 square roots of 2. Whew. Okay, so we get x squared times x plus 2 plus 2 square roots of 2 times x plus 2 minus 2 square roots of 2 is equal to 0. So the roots, which is another name for the zeros, are x is equal to the set 0 plus negative 2 plus or minus 2 square roots of 2. Oof. So we've got factoring, and I guess we also have the quadratic formula too. Let's take a look at another factoring problem here. I've got g of x is equal to x cubed minus 2x squared plus x. I'm going to find the roots of this. So I'm going to say x cubed minus 2x squared plus x is equal to 0. Well, everything has an extra factor of x in here, so I'm going to pull out that factor of x. What's going to be left is x squared minus 2x plus 1, and that's equal to 0. Oh, this bit in the parentheses here, I certainly know how to factor that. I recognize it. I know that x minus 1 times x minus 1 is equal to x squared minus x plus 1. It's equal to x squared minus 2x plus 1. Okay then, so I guess that means that this is x times the quantity x minus 1 squared is equal to 0. Now, from this right here, we're going to get that x needs to be 0. And then from this right here, we're going to get that x has to be equal to 1. So what are our roots? X is equal to 0 or 1. And we'd call this a repeated root. Because this is squared, it effectively has two roots at 1. And if you're going to be graphing these functions, that's important to know, because it means this graph looks like a parabola at x equals 1. So at x equals 0, it's 0. We'll just sketch this out really quickly here. It goes through here, 0, 0. And then at 1, it's a parabola. So, and this is a sub 3 equals 1, which is greater than 0. So that means it's going to have this kind of behavior, right? Going back to what we were talking about. So my long-term behavior is something like this. And now I need to connect these dots. I need to start down here. I need to pass through this point. And then I have to go like a parabola over here. So I start down here. I pass through this point. To go like a parabola, I have to turn, go like a parabola, go like a parabola through that point at 1, and then go on out. And this is the point 0, 0, and this is the point 1, 0. I might find this just to try and get an idea of what 1/2 and then g of 1/2 is. That might be helpful. And that would be a pretty decent sketch of this this polynomial. Intermediate value theorem talks about what happens in between 2 points. And this quick graph that I just did, an extension of the intermediate value theorem would be that I know that there's it's got a turn in between these two. It's 0 here, the height is 0 right here, the height is 0 right here, 0, 0. So then right up in here it has to turn. That's an extension of the intermediate value theorem. Another one would be, if you recall this one, we've got these roots at -2 plus 2 and -2 minus 2. There's got to be a 0 on either side of -2 plus 2 square roots of 2. That is to say, if I pull up my calculator and I take -2 and I add to it 2 second square root 2, and I hit enter, and I look at f of 1/2, so this is 0.83, call it. F of 0.8 and f of 0.9. 0.9 to the 4th plus 4 times 0.9 cubed minus 4 times 0.9 squared. F of 0.9 is 0.33. Let's figure out what f of 0.8 is. I'm going to go in here, I'm going to replace these 9s with 8s. See, one more to go. I've replaced the 9s with 8s. I'm going to hit enter, and it's negative. It goes from negative to positive. So the intermediate value theorem says, here's the line y equals 0. If over here I'm less than 0 and over here I'm greater than 0, then somewhere in between I must be equal to 0. That's the intermediate value theorem. So I know that between 0.8 and 0.9, between where it's negative and where it's positive, this function f of x must be equal to 0. Otherwise, it just kind of jumps. And remember what we said? Way back when we were talking about what polynomials are and what their graphs look like, we said, no jumps. So if we've got a polynomial, if we've got something continuous, it's got to follow the intermediate value theorem. I'm going to show that there's a 0 between 2 and 3 for f of x equal to x cubed minus 2x minus 5, and we're going to do it the same way that we did before. I'm going to take f of 2, that's 2 cubed minus 2 times 2 minus 5, that's 8 minus 4 minus 5, which is -1. And then I'm going to take f of 3, that's 3 cubed minus 2 times 3 minus 5, so that's 27 minus 6 minus 5, which is 16. F of 2 is less than 0, is less than f of 3. So somewhere in between 2 and 3, there is some value that makes this 0. I'm going to write this all mathy like there exists r such that 2 is less than r is less than 3, f of r is equal to 0. Why r? Root. You could also use z for 0. So there's some number out there that's between 2 or 3, and f of r is equal to 0. Cool. Now, let's talk about turning points for graphs. When I was drawing G here, I had it make 1, 2 turning points. And notice how G is third degree. Third degree two turning points. So the number of turning points is 1 less than the degree. They're hard to find without calculus. I made some sort of guess that, oh, well, we could take g of 1/2 and put it in there and kind of see what that value is. That wouldn't really tell us where the turning point is. We need to find it, and we need to prove that it's a turning point. And that's pretty hard, the proving part of it. That's what's really hard without calculus. We can get approximately there, but we need some calculus to show us where the slope is equal to 0. Then we can find turning points right easily. So for now, I would say we plug some numbers in and we guess. We want to get close. After all, if we really need to know what a graph looks like, we've got one of these hanging around. Or even better yet, we've got the internet kicking around. We've got Excel. We have tools. We have computers that will tell us the values for graphs. But we can also use our brains to figure out whether those are reasonable or not. I want to go ahead and I want to graph a function, and I'm going to start with the function f of x is equal to negative x to the fourth plus 4x squared. Now I've got my axes, but I'm in no way ready to graph this yet. First thing I want to do is I want to find just the overall shape of it. So what degree is this? Fourth degree. This is degree 4, which means we're going to have 3 turning points. We'll just call it 3 turns. What's the leading order coefficient here? The leading order term is negative x to the fourth. N is even, and a sub n is less than 0. So what shape is that? This double down shape. 2 thumbs down. It's a double down shape. I think next we need zeros. We need some zeros. We need some roots for this function. I'm going to say 0 is equal to negative x to the fourth plus 4x squared. I'm going to factor out negative x squared. And if I factor out a negative x squared, you know what's left? X squared minus 4. And here's the thing about x squared minus 4. X squared minus 4 factors into x minus 2 and x plus 2. So to find these zeros, I went ahead and I factored. And this got me the zeros, negative 2, 0, and positive 2. Those are the zeros of this function. I think I've got a pretty good handle on what's going on, and I'm ready to graph this. But you know what? I'm just going to find some points so that I know what this graph is doing. F of 1 is a pretty good example. So negative 1 to the fourth plus 4 times 1 squared. That's negative 1 plus 4. F of 1 is 3. You know what? I'm going to find f of negative 1 while I'm at it. F of negative 1 is negative 1 to the 4th plus 4 times negative 1 squared. That's negative 1 plus 4. F of negative 1 is also 3. That's pretty good to know. We've got some symmetry. I think f of 3 is going to be too big huge, but let's check. F of 3 is negative 3 to the 4th plus 4 times 3 squared. This might fit on our axes here. 3 to the 4th is negative 81, and then this is going to be 9 times 4, so 36. This is not 50, but 45, negative 45. Yeah, I knew that was going to be off the scale, but still. Wow, that's way off the scale. Let's take a look at our axes here, and we need the zeros at negative 2, 0, and positive 2. So our zeros at negative 2, 0, and positive 2. Great. And then we had our points 1, 3, and negative 1, 3. Okay. 1, 3, and negative 1, 3. Now I don't know that these are the turning points, and I kind of don't want to make them the turning points, but they really could be the turning points. As a matter of fact, at 0 here, I'm pretty sure that's a turning point. Oops. At 0, I'm pretty sure this is a quadratic because it's squared. I'm pretty sure it's going to make a parabola there, and then these are going to be linear because they're just to the first power. So that's linear, and this is quadratic at 0. So, oops, I keep doing that. Over here, I'm thinking this is going to be kind of quadratic. And then here, I'm thinking it's linear, and here, I'm thinking it's linear. So these are totally turning points. I may as well call them the turning points. I'm sketching in the shapes that I want to have. And then negative 3, by the time it gets to negative 3, it's going to be way negative. By the time it gets to 3, it's going to be way negative. So I think I've got a pretty good shape for my graph. I'm going to go ahead and I'm going to draw it in. So I'm going to come down here, way negative. I'm going to hit this point, pass through it like a line, come up over here, turn, come down, turn, come up, turn, come down, and then go way negative. And it's shaky and it's wiggly and it's wobbly, but it's pretty much accurate. And if I want, I might label this point as 1, 3. I might label this point as negative 1, 3, and I might say f of 3 is equal to, what did we figure it was? Negative 45? Negative 45. So way down here off the end is 3, negative 45. And again, the overall shape of this is kind of a weird letter M type thing going on. Alright, that's it for this section. That's a good overview. I'll be back in the next videos with some more worked examples. Thanks and good luck.